Hi students, so welcome to another video on control systems. So in this video we will see steady state error for a given control system. Let us see this initial slides. Okay, if you are ready, we will start. So let us consider a control system having input as RFS and having a forward transfer function GFS. So let us consider a unity feedback system, so where HFS is equal to 1 and this is having a negative feedback, and we know that output is CFS. So the same CFS is fed back here, so this is a summation point, and we know that this is the error signal, so this is EFS. So we are mainly looking at, so what is this error EFS? Now since the topic is steady state, so the topic what we have is steady state error. So let us try to understand what is this steady state error definition and all those stuff. So we are looking at steady state error, and it is abbreviated as, it's an error signal in steady state. So which is nothing but the error in time response as t tends to infinity, which we can write it as E infinity. Since t is tending to infinity, so this is E of infinity is the error signal, and as t tends to infinity, whatever is the error, I'll call it as steady state error. So when I say steady state, once the system has settled to a typical value, we call it as steady state error. So after steady state, there will be no usual change in the state of the system. That's why we call it as steady state error. So in a control system, we know that we actually apply a input voltage which is the desired output itself. So I can typically say error of a system is nothing but how much it is deviating from the expected value. So my expected output finally is R of t, the actual output is C of t. The deviation from the expected to the actual is nothing but the error, Just a minute. What is the error signal is. So error signal in general can be written as difference of the expected output, which happens to be the input for a general system, R of t minus C of t. C of t is the actual output of the system. So now in this a unity feedback system, for a special case of where you have a unity feedback system, so this, okay, if I call it as this as BFS, so now this whatever is error signal, shall I say this error signal whatever you have it here, this C of t and this B of C are same. So shall I now replace this C of t from this block diagram? Can I write the error signal, that is this error signal, as R of t minus the feedback signal B of t, that is the feedback signal. Since B of t is same as C of t, or if you take the Laplace of it, I can write EFS is nothing but RFS minus BFS. So what is BFS? BFS is nothing but CFS. I can write it as RFS minus CFS. But this CFS, which is same as BFS, is nothing but EFS into GFS. So I can replace this by GFS into EFS. So ultimately this will become EFS is equal to RFS minus GFS into EFS. Upon rearranging, let me take this GFS into EFS onto left hand side. Can I write it as EFS? This minus, if I take it onto left hand side, it will become plus GFS into EFS, which is equal to RFS. So what is EFS now? EFS, if I take it outside, it will become GFS, and this is equal to RFS. So from this I can write EFS error signal is nothing but RFS by 1 plus GFS. So this is true when it is a unity feedback system. So for a unity feedback system, I can write error signal as RFS by 1 plus GFS into HFS, provided it's unity feedback, and unity feedback is the magnitude, and it's a negative feedback, We know that this is just the error signal. So we also know that the steady state error is nothing but limit of t tending to infinity EFT. So that's what is this. Using final value theorem of Laplace transform, I can write it as limit of s tending to 0 s into EFS. If I know the Laplace of this error signal, the steady state error, which is defined as limit of t tending to infinity, that is as t tends to infinity, what is EFT, can be written using the final value theorem as limit of s tending to 0 s into EFS, where this EFS is Laplace of EFT. So I can write this ESS as equal to, that is, let me substitute what is EFS from this. So is this not limit of s tending to 0 s into, what is EFS? It is RFS by 1 plus GFS. So this becomes your equation for steady state error. So this is 1 plus GFS. Suppose in general, if you write the steady state error, this is steady state error, ESS is nothing but limit of s tending to 0 s into RFS by 1 plus GFS. You can still write GFS into HFS. Make sure that this HFS is 1. So this is the expression for steady state error of any system having GFS as the forward transfer function and HFS is equal to 1, and it's a negative feedback, and input can be any input, any standard input like step, ramp, or it can be a parabola. So with this definition, let us try to find what is steady state error for different systems having different possibilities of poles and zeros. Now let us define what are these inputs. So let us talk about what are the standard input. Any typical input that is possible are divided into, or it will be a combination of various standard inputs. There are 3 standard inputs that will be considered in this case. So those 3 are unit step input, or you can call it as a step input. Of course unit is just the magnitude. Step, it can be a ramp input or it can be a parabolic input. So when you say step input, it is with respect to time, so it will be like this. So suppose if you say this is t equal to 0, so till t is equal to 0, the output is, the magnitude will be 0. Afterwards it goes to a magnitude of some x value if it is some amplitude. If it is unit step, then it is of magnitude 1. At t equal to 0, it is 0. For t greater than 0, it is always 1 for a unit step input. Sorry for the inconvenience. So this R of t will be u of t. So this u of t is equal to 1 for t greater than or equal to 0. So what is its Laplace? R of s. The Laplace of a unit step input is 1 over s. For any other input, this 1 will become whatever the magnitude. Suppose instead of this unit step, if it is of magnitude 5, this will become 5 by s. If the magnitude is 10, it is 10 by s. If it is a ramp, this is how the amplitude is keep increasing with a slope of 1 or whatever the value you are talking about. Now what is this R of t now? The R of t is actually equal to now t. Now where if the slope is 1, if the slope is different, it can be greater than 1 or less than 1, so it will be 3t, 4t, or it can be 0.6, 0.7 t. So what is its Laplace? Its R of s is equal to 1 over s square, depending on what is the slope of this line. So similarly, we have parabolic, which is going like this. This is with respect to t. Now R of t is taken as t square. If it is t square, we know that Laplace of that is 2 by s cube. 2 by s cube. So in order to make this magnitude in the numerator as 1 over here, actually the typical input is taken as t square by 2. So it will be typically taken as t square by 2. So when it is t square by 2 is your R of t, then R of s becomes 1 over s cube. So standard inputs are its R of s. For unit step input is 1 over s. For a unit ramp input it is 1 over s square. For a parabolic input, which is t square by 2, will be 1 over s cube. This is for t square by 2. This is for t as your R of t, and this is like u of t. This is like u of t. So these are the possible inputs you can consider for this R of s. This R of s for finding ESS, of a system. Now comes, this is about the input, then comes about the type of a system. This is type of a system. So when we are talking about type of a system, so you might have seen that when we are actually finding the ESS, we are writing limit of s tending to 0, s into R of s by 1 plus g of s. Of course, h of s is equal to 1. So you are talking about g of s, which is nothing but the open loop transfer function, which is nothing but g of s into h of s, and it's equal to g of s for a unity feedback system. This is open loop transfer function. So now, looking at the open loop transfer function poles, we define type of a system. So assume that you have GFS of a system as 10 by s plus 4. So now looking at this, the open loop is at there is an open loop pole at -4. So this is defined as type 0 system, because type of a system is nothing but how many open loop poles are there at the origin of this S-plane. So type of a system is nothing but number of open loop poles at the origin. Suppose if you don't have any open loop pole at the origin, then it is called as type 0 system. Type 0 system means that you don't have any open loop pole at the origin. So similarly, you have type 1 system. So this type 1 system will have one open loop pole at the origin. For example, so I can write it here. So type 1 may be something like 10 by or 100 by s into s plus 2 s plus 6. Now irrespective of the number of poles, we are looking at how many poles are there at the origin, how many open loop poles are at the origin. So this is actually GFS. This is GFS. For a GFS which is 100 by s into s plus 2 into s plus 6, so where are the poles now? One of the pole is at origin, other pole is at -2, one more pole is at -6. So we have 3 poles, out of which, of course, 3 open loop poles, out of which one is there at the origin. So this is called as type 1 system. Similarly, type 2, suppose you want to write it, modify this itself, or if I want to write it for type 2 system, type 2 can be, so it can have, of course this is GFS, which will be maybe 3 by s square into s plus 1. So now if you see here, how many open loop, this is just GFS, how many open loop poles are there at the origin? It's 2 open loop poles. So you just write it as repeating poles at the origin, and you have one at -1. So whether you have the other poles wherever they are, if there are 2 open loop poles at the origin, it is type 2. If it is 1 open loop pole at the origin, it is type 1. If there are no open loop poles at the origin, it is type 0. So it is type 0, type 1, type 2 for the system. Now let us consider a type 0 system, and let us consider the inputs, the input step, ramp and a parabola. So let me consider GFS as, let me say it as GFS into HFS, but HFS is equal to 1, so I can write it as this as some 10 by s plus 6. So what is the type number now? Type number is 0. So this is a type 0 system, For this, let us take input r of t as a unit step function, where r of s will become 1 over s. So let us try to find what is ESS for this. So what is the definition of your ESS? It is nothing but limit of s tending to 0, s into r of s by 1 plus GFS into HFS. So now what is this? Limit of s tending to 0, s into, what is r of s? It is 1 by s divided by what you have in the denominator, 1 plus GFS. That's what you have here. Of course, GFS into HFS is 1, it is so and so. So does this 1 go with this? So now what you have? It is limit of s tending to 0, 1 over 1 plus, what is GFS? It is 10 by s plus 6. Now since I have the limit of s tending to 0 for the entire thing, since there is no s here, there is no s here, so there is only s over here. So let me write this as 1 over 1 plus limit of s tending to 0. Let me write this as GFS only. Let me write it as GFS. So GFS in this case it is 10 by s plus 6. Now we define this term, which is limit of s tending to 0 GFS as proportionality error constant, error coefficient or error constant. So Kp is now defined as proportional error coefficient or constant. So now what is this now is given by 1 over 1 plus Kp. Now whatever the type of the system, if the input is a unit step input, we can find what is ESS. ESS is nothing but limit of s tending to 0. I'm just making this RFS as equal to, because what was our ESS? Let me write ESS here. ESS is nothing but limit of s tending to 0 s into RFS by 1 plus GFS. So in place of RFS I have substituted 1 over s, so we end up with ESS as given by 1 over 1 plus Kp, provided the input is a unit step input. So okay, let us take this example, specific example bit later. Now let us consider a ramp input. When I consider a ramp input, so what is the ramp input you have? For ramp input you have R of t as equal to t, so R of s is 1 by s square. So what is ESS? ESS is equal to limit of s tending to 0 s into R of s by 1 plus GFS. Of course h of s is 1. So let us substitute the value of R of s, which is 1 over s square. So can I write it as limit of s tending to 0 s into 1 over s square by s into, sorry, s plus, sorry, it is 1 plus GFS. Does this go with this? Do I have it as limit of s tending to 0 1 over s into 1 plus GFS? I can further write it as limit of s tending to 0 1 over s into GFS. Now you apply the limit of s tending to 0. Does this become 0? This becomes 0. So now is it not 1 over limit of s tending to 0 s into GFS? So now this exclusive value, that is limit of s tending to 0 s into GFS, is called as KV. This is called as KV. So this KV is nothing but, for Kp it was proportional error coefficient. Now this KV is error, it is velocity error coefficient. KV is now velocity error coefficient or constant. So what is KV now? KV is nothing but limit of s tending to 0 s into GFS, because you can write GFS into HFS, but HFS has to be 1, So this is for a ramp input. If the input is parabola, suppose now take the input as R of t as t square by 2, which is a standard parabolic input. So then what is R of s? It is 1 over s cube. So therefore, what is ESS? ESS is now given by limit of s tending to 0 s into r of s by 1 plus GFS, 1 plus GFS. Substitute the value of s as 1 over s cube. This will become limit of s tending to 0 s into 1 over s cube by 1 plus GFS. This will go with this and it will become square. Now it is limit of s tending to 0 1 over a square plus s square into GFS. When you apply that limit of s tending to 0, this will go to 0. Therefore, ESS for a parabolic input is 1 over limit of s tending to 0 a square into GFS. This we call it as this exclusive term. This exclusive term we call it as KA, acceleration error constant. So this is now KA now, acceleration error coefficient, efficient or constant. So this is my, so what is KA? KA is given by limit of s tending to 0 s square into GFS. This is the acceleration error coefficient. Now let us take different type system, try to find out what is KP, KV, KS using an example. So let us take the same example, which was GFS was taken as, what we have taken as s plus, let me take it as GFS as 10 by s plus 6. So this is a type 0 system. Let's just consider R of t as a unit step. So its R of s is 1 over s. So we know that whenever it is a step input, or let me just summarize here, if it is a unit step input, ESS is 1 over 1 plus KP. That's what we had here. This is what is ESS for a step input. For a ramp it is 1 over kV. For a parabolic it is 1 over KA. This is actually 1 over KA is ESS when you have a parabolic. So this is when it is unit step. If it is parabolic, it is 1 over kV. Sorry, if it is ramp, if it is parabolic, it is 1 over KA. Since it's a type 0 system, the input is a unit step. So what is ESS? ESS is 1 over 1 plus KP, because it's a unit step input. What is KP? KP is actually equal to limit of s tending to 0 GFS. So what is GFS? In this case we have taken GFS as, so it is limit of s tending to 0 10 by s plus 6. So for this case, since it is, if it's tending to, s is tending to 0, now I'll apply that limit of s tending to 0, this becomes 0, so this becomes 10 by 6 is my KP. So KP is now equal to 10 by 6. So what is ESS? ESS now is equal to, as per this, 1 over 1 plus 10 by 6, which will be 6 by 16. So this is the steady state error, which is a finite value for a type 0 system. So summary is type 0, u of t as the input, the error is finite. So let us take the same type 0 system, let us apply a unit ramp. So what is GFS? GFS is still 10 by s plus 6. It's a type 0 system, but consider R of t as t, which will result in R of s as 1 over s square. Let us go with ESS, which is nothing but limit of s tending to 0, s into R of s by 1 plus GFS. So this is a general thing. Since the input is parabolic, we saw when the input is parabolic, which is this, when the input is RAM, what are the ESS? It is 1 over kV. So shall I write ESS as equal to 1 over kV for a ramp input? Yeah, this is T. So but what is kV? It is actually limit of s tending to 0, s into GFS. So let me apply that for this example. S into what is GFS? It is 10 by s plus 6. So when you apply that limit, this becomes 0, because 0 by anything is 0, so it is 0. So kV is 0. When kV is 0, what is ESS? ESS is nothing but 1 over kV, which is nothing but 1 over 0. This will become infinite. So the summary is, for a type 0 system, if you give a ramp input, the steady state error is infinite. So let us take the same type 0 system. Let us consider a standard parabolic input. So this GFS is again still 10 by s plus 6. You take a type, this is a type 0 system. So let us now consider R of t as t square by 2. This results in a R of s of 1 over s cube. So we know that if it is a standard parabolic input over here, so the ESS is 1 over K. So what is ESS? ESS is 1 over KA, but KA is nothing but limit of s tending to 0, s square into GFS. So let us try to find what is KA for this particular example, which is now limit of s tending to 0, s square. GFS is actually 10 by s plus 6. If you apply the limit of s to 0 here, so now this will become 0 by 6, which is nothing but 0, So this is KA. Then what is ESS? ESS is nothing but 1 over KA. So this is 1 over 0. This is now infinity. So the summary is, for type 0 system, if you have a step input, you will have a finite error. For a same type 0 system, if you give a ramp, error is infinite. If you give a parabolic, error is infinite. So if I write the table where you have the input, it is type of a system. Now the input is u of t type 0. It's a finite error. Now it's a t, the error is infinite for type 0. For an input which is t square by 2, which is a parabolic, the error is, this is my ESS. So this is whatever that I'm filling here is for ESS. So for ESS, with this input, this is input, this is type number, this is type 0, so on. So let us do it for type 1. So when you consider type 1, so let us consider the type 1 as, maybe you can take an example where you have one pole at the origin, one open loop pole at the origin. So GFS, let us take it as 25 by S into S plus 1. So this is a type 1 system. So what is ESS for a step input? It is 1 over 1 plus Kp. So what is Kp? It is limit of S tending to 0 GFS. So what is GFS in this example? It is limit of S tending to 0, 25 by S, this one. So can you see this is 0 here? So when you apply that limit of S tending to 0, the Kp will become 25 by 0, which is infinite. When this is infinite, so what is ESS? ESS is 1 over 1 plus infinity. This will become 0. So for a type 1 system, if you have a unit step input, the ESS is 0. The ESS is 0. Again, take same type 1. This is a type 1 system. This is a type 1 system. Let us consider the input which is, let me write it in a different pencil. It is 1 over, this is a ramp input. For a ramp input, it is 1 over kV. So what is kV? kV is nothing but limit of S tending to 0, S into GFS. So let us take the example of GFS as this type 1 system. So is it not limit of S tending to 0, S into 25 by S into S plus 1? So does this S go with this? So if I apply the limit, is it not 25 by 1? Is it not 25? Is this not my kV? So what is ESS? ESS is 1 over kV. Is it not 1 over 25? Can you see the ESS is a finite value? So for a type 1 system, if the input is ramp, I will end up with a finite error. This is my finite error. So let us take the same type, and if you consider what is ESS for? ESS for a R of t, which is t square by 2, which is a standard ramp input, which will end up with a R of S, which is 1 over S cube. So we know that ESS for such a system is 1 over Ka. What is Ka? Ka is nothing but limit of S tending to 0, S square into GFS. So what is GFS now? It is 25 by S into S plus 1. So this square will go with this, and when you apply that limit, this Ka becomes 0. When this becomes 0, what is ESS? ESS is 1 by 0. This will become infinite. So for a type 1 system, if the input is parabolic, which is t square by 2, the standard one, you will end up with a ESS of infinity. So this is infinite. Type 1 parabolic input, error is infinite. So let us now consider type 2 system. This is type 2 system. When you have a type 2 system, for different inputs, let us see what happens to the ESS. So what is GFS for a type 2 system? Let me take it as some 5 by S square into S plus 2. So this is a type 2 system because it has got 2 open loop ports at the origin. So this is now type 2 system. For a step input, what is error? It is 1 over 1 plus Kp. What is Kp? It is this. So Kp is nothing but limit of S tending to 0 GFS. So what is GFS? It is 5 divided by S square into S plus 2. So what is this now? So since S is tending to 0, this will become infinite. So when this becomes infinite, so what is ESS? ESS is 1 over 1 plus infinity, it is now 0. So for a type 2 system, if the input is a step input, the error is 0. Now for the same type 2 system, let us apply an input which is ramp. So its ESS is 1 over kV. kV, we know that its limit of s tending to 0, s into GFS. So what is this now? Limit of s tending to 0, s into GFS is what? 5 by s square into s plus 2. This square will go with this. So this will again become infinite, because 5 by 0 is infinity. So this is kV, which is infinity. So naturally ESS will become 0. So for a type 2 system, if the input is a ramp, which is something like this, this is T now, we'll end up with the ESS of 0. This is ESS 0. So let us again take same type 2 system. Let us consider R of t as t square by 2. So where R of s will become 1 over s cube. So what is ESS of this? ESS of a parabolic input is 1 over Ka, where Ka is given by limit of s tending to 0, s square into GFS. So what is this GFS? This is limit of s tending to 0, s square. GFS we have considered as 5 by s square into s plus 2. So then this square will go with this. If you apply the limit of s minus 0, this will become 5 by 2 is the value of Ka. So then what is ESS? ESS is equal to 1 over, this is actually 2.5, this will become 2.5. So it is 1 over 2.5. So ESS is nothing but 1 over Ka. Since Ka is 2.5, this is 1. So now if you want to fill the table for a type 2 system, which is having something like this. So this is what is type 2 system, which is 5 by s square into s plus 2. So you will have a finite error for a parabolic input. This was my parabolic input. Can you see there was a finite error which is 1 over 2.5, which is 0.4, which will be 0.4. So I have a finite error. You had a 0 error. You had a 0 error. That's what it is 0. For a type 2 system, for unit step and ramp input, the error is 0. But for a parabolic input, you will have a finite error depending on what is the magnitude. What is the magnitude? So this is about the steady state error of a system, especially when the system is a unity feedback system. This is when it's a unity feedback system. So when the feedback section is 1, this feedback section is 1. So we will see in the next video few more problems on this, and then we will also see what is ESS if the system is a non-unity feedback system. The system is having some non-unity feedback.